today I will introduce a perception-driven approach for the high-dimension data visualization. High-dimension data is quite common in many application domains. To visualize such data, dimensionality reduction, DR, is a common strategy to reduce data while keeping data visual interest. Right now, actually, like using this example, actually right now we have many DR methods. So many methods developed by machine learning, data mining, or statistics. However, on the other hand, one of the most important tasks in high-dimension data visualization is to inspect how classes or clusters are separated. Let's see how this method works. This example. These two results actually generated by unsupervised method, PCA and MDS, and these two results generated by supervised method, LDA and KDA. Here you see, using most of classes are not perceptually separated. After careful investigation, we think the main reason actually is that these methods are developed by machine learning guys. Actually, they work in data space, rather than consider all perceptual factors. We are visualization guys, we are working visual domain, but they didn't provide help for us. So to fill this gap, we propose a perception-driven dimensionality reduction approach. Here we are saying, if we incorporate perception factor to dimensionality reduction model, we can generate results with class which are well perceptually separated, like this example. Okay, now I'm first focus on linear dimensionality reduction, which is easy to understand for most users. Given an n-dimensional data point, we are trying to find a linear transformation P that map high-dimensional data point to a low-dimensional space. Now let's see our formulation. You can see here actually we are trying to maximize visual class separation value by finding a projection matrix P. Here actually SYI is it can be any kind of visual class separation degree for point in low-dimensional space. As you may see, our method is based on the visual class separation methods. Fortunately, our community have did a very good work. Sandemeyer and Aptitude. In 2015, they did a systematic study. They found that the best measure is a decent consistency called DSC. And later, actually, this same also designed 2002 new visual separation measures, and they did a study again. They find GONG is the best, but they recommend the other one. This was the KNG, they called KNG because of the high performance. Let's see how this measure works. I will first talk about decent consistency, DSC. In this measure, actually, for each point, it computes a within class distance with its own class center, mu1, and then consider between class distance, yi to mu2. Here, once we have these two distance, it compare these two distance, and if the within class distance is larger, then the separation degree is 1. Otherwise, it's 0. Finally, we take average of all these point value as the final DSC value. So the time complexity of this measure is O of n log C. Here C is the number of classes. Yeah, actually, Michael Sadima showed that this measure actually is not the best one. Let's see how the best measure, GONG, works. Actually, this measure works in 2 steps. First, it constructs a gamma observed graph by finding intermediate point, as here you see showing green point. Once this graph is ready, it computes the separation degree by check how many neighborhood points have the same label. This measure performs the best. However, the construction of gamma observed graph is very expensive, where the time complexity is O of n squared log n. So that limits its usefulness. The other measure recommended by author is KNG. This measure uses the same equation to compute the separation degree for each point, but it's based on 2 nearest neighbor graph. So you may know, construction of 2 nearest neighbor graph, the time complexity is quite low, just O of 2n log n, which is good for us to use. Hence, we are wondering if we directly use these 2 measures, DSA or KNG, to drive perception-driven dimensionality reduction, what kind of result we can get? Let's see. We did an experiment. Here you see, the left one is driven by original DSC, the right one is driven by original KNG. You may see that actually this is the class structure in these 2 results are still not well separated. That's true. We think the main reason is that these two measures actually don't consider the class density information. Also, they work well in the previous test. Let's see an example. The left one and the right one, they are two scatter plot, but you see the totally different kind of class structure. The left one, well, two clusters are scattered, and their boundary are mixed together. You see these 2 points, while the right one, they are well separated, and the class structure is very compact. However, you see the DSA value very similar. So this is nonsense. So we think it's possible to improve this measure to consider density information. Actually, that's quite easy. We still compute the within class distance and between class distance, but then we use these two distances to compute the separation degree, rather than just compare them. As you see, we define the separation degree as the difference between these two within class distance and between class distance, and then normalized by the maximum distance. Now let's see how the result can get. Now the left one is 0.63, the right one is 0.73. Now I think you may agree that this is reasonable. Say likewise, K and D have the same problem. Let's see. Here B and D, these 2 points. As I said, the 2 nearest neighbor graph. And B and D have similar pattern. The one nearest neighbor is the same label, and the other neighbor is a different label. So they have the same K and D value. But you see, the B actually the most nearest neighbor is A, which have different label. While for D, most nearest neighbor is E. They have same label. Moreover, the distance DE is smaller than AB. So they have same separation degree is nonsense. So we think, how can we improve that? Let's see. Actually, we take a similar idea we work for density over DSC. Here we say we also measure within class distance and between class distance, AB, BC. And then we use this distance to compute the separation degree. Actually, the same equation as the density over DSC. And now let's see what kind of value we can get. Here you see. For B right now, the density over KNG value is minus 0.23, while for D is 0.95. I think you agree with me. For B, actually, the most nearest point is A, which have a different label. It should be a minus value. Okay, now we address this case. Actually, KNG has another 2 cases. Let me show. Here you see B have another label. With another point with same label, we set the separation degree as 1. If you have different label, we set the separation degree as -1. Okay, now you see the range of DKNG value is between -1 to +1. Okay, now we have the density aware measure. We are thinking it's possible to directly use them to drive our perception-driven dimensionality reduction. Now we need to solve this optimization function. Okay, to solve this optimization, we customize our similarity annealing algorithm as shown in this here, algorithm 1. Actually, in this algorithm, there are 2 major components. The first one is the set initialization of P. In our experiment, we found random initialization is good for most of data. The second part is to selection of neighborhood solution code from P. Here, actually, it's done by a random process. We draw a random value for each point, and then check it is greater than a given threshold. If larger, then we search for local optimum. Otherwise, we add a random offset. This try to generate global optimal values. As you may see, the threshold E is very important. A smaller E might result too many local optimal computation, while a large E will lead to small number of iterations, and generally the result is quite poor, as you see the last one. So in our experiment, we found set E as 0.5 is quite good for most data. Okay, finally I will talk about the time complexity. For short, I call the perception-driven DRR method using density over DSA as PDD, the other is PDK. The time complexity of them are O of dmn and O of dmn log n. Here n is the total number of iterations. Let's see how these 2 methods converge. This plot shows the convergence curve. You can see PDD gradually converts, while PDK quickly arrive at a reasonable solution. Now, we're going to talk about the evaluation part.
Okay, Now let's talk about the evaluation of our methods. We compared our approaches PD, PK, PDD, PDK with 6 existing DR methods. For the datasets, we collected 93 labeled high-dimensional datasets. We used box plots to show the result of the comparison. We choose 2 measures for this numerical comparison, GONG and SC. Here the blue box plots show the score over all 93 datasets, and the red box plots describe the score of the real datasets only. It is clear that PDD and PDK perform better, especially in real datasets. Next, we perform a more detailed qualitative comparison on the top 4 methods. We can see that the class structure generated by PDD and PDK are more compact. On the other hand, we evaluate PDD and PDK in terms of human perception. Let expert coders read scatter plots in terms of how well they think the classes are visually separated. We do not include the methods of PD and PK because their results are worse than PD and PDK as shown in last box plot. We compute the average separability rating of each method over all datasets and over only real datasets. We can see that the PDD and PDK perform well regardless of the data category. We compare the performance of our methods against the LDA and Disney, where all are implemented in C++. The result is shown in box plots. And you can see our PDD is usually faster than Disney and takes less than 0.1 seconds for most data. And for PDK, it's closer to Disney, but much slower than PDD. Our methods can also be extended for exploration of class imbalance data and the classification of unlabeled data. The class imbalance data is where some classes have many samples and others a few. If we directly apply DR methods to them, the separation will bias towards the classes with more samples. To alleviate this issue, we allow the user to normalize the separation degree SYI by number of points and C. We call this method the weighted PDD. You can see that the result generated by weighted PDD is more compact than result generated by PDD. Our method can also be used for progressive classification of unlabeled data. Taking PDD as an example, we first randomly sample a small subset of items and present it to the user for labeling. Apply PDD to the labeled data. Classify the remaining unlabeled data and project all data points. These steps are iteratively pursued until the user reaches a desired result. Let's see an example. We can see that the accuracy gradually improves as the number of label samples increases, and the accuracy generated by PDD increases more quickly than that generated by LDA. Our approach still has certain limitations. First, PDK's computation cost is still expensive. Try to make it lower is one important thing first. Second, although PDD outperforms the other for most data, for some datasets, it results in interclass distance that are smaller than those of PDK. So we plan to reformulate the DDSA by putting more emphasis on interclass distance than intraclass distance. Third, we would like to investigate the possibility of semi-supervised methods for interactive classification of unlabeled data. Thank you very much. And any questions?